Hello, everyone. So I'm going to kind of walk through the notes over these next couple days. The completed key is already up online, and you guys can always look at that and try these problems on your own. But I'll more just walk through. And if you want any more specific instruction on it, you can always feel free to email me or send a message on Zoom, and we can talk there. So this first problem we look at: does seat location matter? Many people believe that students learn better if they sit closer to the front of the classroom. Does sitting closer cause higher achievement? Or do students just choose to sit in the front? To investigate, an AP Stats teacher randomly assigned students their seat location in his classroom for a particular chapter and recorded their test score for each at the end of the chapter. The explanatory variable in this experiment is the row the student was assigned. So here are the results. You'll notice those sitting in the first row scores, second row, third, fourth, and so forth. Okay, we look at our scatter plot here. Your row that you're sitting on was your explanatory. The score is your response. And we're looking at that relationship there. You can see they give us an equation right here. They say the score, okay, remember this is your predicted score. You can put your little hat on top there, is equal to 86 minus 1.12 times the row. Okay, so that means that 86 is your intercept. That negative 1.12 is our slope. And if we remember about r squared, okay, 0.047, that means 4.7% of this variation in test scores can be explained by the row, which is not a very high amount there. The first question they asked is about causation. What allows us to conclude causation about, and also about generalizing to the population? Remember, correlation does not mean causation. Okay. We can conclude causation, again, as long as the experiment has randomly assigned treatments. Okay. So as long as the experiment has these randomly assigned treatments, we can conclude causation. So in this case, you were randomly assigned a seating location, because that case would be our experiment here, our treatments. And then in order for this to be about the population, okay, we need to take a random sample from the population. Again, I've talked a little bit. This section is not going to be on the AP test anymore, but really what we're doing right now is reviewing Chapter 3, linear regression, so it's still a very good thing for us to look back at. Next, interpret the slope of the least squares regression line in context. Well, we already saw that the slope was negative 1.12. Just basically saying for each additional row, okay, so as r goes up, means we're getting further from the front of the room, a student's test score is expected to drop by about, remember that keyword, about 1.12. Does a negative slope provide convincing evidence that sitting closer causes higher achievement, or is it plausible that the association is due to chance variation? Okay, that's really what we've been just talking about all semester. Are the results we got usual or unusual based on what we know? Okay, and we always kind of go in assuming that there is nothing. It's zero. The row doesn't change anything. Well, if we look at this table here, this is a table of doing this 100 times and getting out a certain slope. So we'll notice it's centered around 0. That negative 1.12 falls right about here, which we see we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 that are more than extreme than that. So it's possible that this is due to chance variation, as it occurred in 11% of those trials above. Okay, so even if the center is supposed to be 0, the true slope, 11% of the time we could get this or more extreme. So we can't really go and say that there's a causation there. Now, if we were to move on and do a test with this, we have some conditions here, some new conditions. Okay, the first one is it's got to be linear, right? We're talking about linear regression. We're not applying this to anything that's exponential or power function or logarithmic. So again, with linear, you want to make sure that you check two things: your scatter plot. If we look up there, it's weak, but it is linear. And then your residual plot, we want to make sure there's no pattern. So we notice here in the residual plot, those points are just jumping back and forth. Okay, we just want to see a randomly scattered design on our residual plot, which means that the linear model is appropriate. And yes, there are 5 conditions. That's just number 1. So I guess a little nice thing that we don't have this on the AP test now, because that's a lot more conditions to remember. Independent. Again, students' test scores are independent of each other. Okay. Again, if this wasn't an experiment, we would have to check the 10%. Is it normal? Okay, so for normal, we check the residual plot of our graph, and we do a residual. Take those residuals and we make a histogram. So if I look at that histogram, that is, oops, sorry, I'm not looking at the wrong graph there. I want to look at my normal probability plot over here on the right. My normal probability plot, the residual is fairly linear. So again, we're good on that spot. Okay. We also check about equal variance. The residual plot shows consistent scattered throughout. What they mean there is our graph keeps bouncing up and down. It doesn't go really close and get far away at ends or anything like that. And then we need to check that we have a randomized experiment, and that's just stated in there for us. So those are your 5 conditions. For the normal probability plot, you can get away with either the normal probability plot, the residuals, or looking at a histogram there as well. So if I want to say that the histogram of the residuals is approximately symmetric. That is another thing that you could look at. Let's move down and do a little work with this here. Here's the computer output. So we've talked about this over here a couple times. And you will see this probably. There's a very good chance you still see this even on this new AP test if they do any linear regression. Okay, remember, these are your coefficients. So the coefficient on my constant, which is my y-intercept, coefficient on my x value, which means it's my slope. We have our S, which is just your standard deviation of your residuals. We have SE, which is your standard deviation of your slope. And then what your test statistic would be and what your p-value would be. And this p-value is for a 2-sided test. Interpreting the slope from there. Okay, well, we made our equations up above. Again, y is the test score. X is the row, so y hat equals 85.706 minus 1.117x. Well, we already interpreted slope earlier, just saying that for each additional row, it's going to go down about 1.12, or in this case, 1.117. Y-intercept would be saying a student who sits in row 0 has a predicted score of 85.706. A lot of times it's not going to make sense, and in this case, it doesn't make sense. Okay. That is a possible question. They'll say, does this make sense in relations to the problem? S, the average error when using our least squared regression line to predict the test scores. So, that's your standard deviation of residuals. How far are we usually off? Well, in this case, our equation usually gives us a value that's off by about 10 points. Pretty large variation there. Okay, your SEB, the standard error of the slope. Okay, is basically saying on average, when we create these least square regression lines, will differ from the true slope by about that much. So if I were to continuously do this, okay, I will be off by about 0.94. My slope will be off that much. Okay, so very likely to get a slope of negative 0.5, as likely as 0.5, varies quite a bit there. And that came from our chart. And the last bit here, calculate the 95% confidence interval for the true slope. Revisit again, confidence intervals, your statistic plus or minus critical value times the standard error. So our statistic is B, critical value is T, and that has a degrees of freedom of n minus 2 because we have 2 variables, x and y there. And then your standard error in this problem is the SEB. So those numbers just get plugged in. To find that t value, you got inverse t of 0.025, because remember with your graph, you're going to have 2.5% at both ends. And we find out that the true slope is somewhere between negative 3.057 and 0.823. If you had your own data, you could run this in a calculator to get that out doing a ln-reg t interval. And again, interpreting like we always do, we're 95% confident the true slope of the least squares regression line for predicting the test score based on your rho is between those two values. So a big thing to think about is, where did 0 fall? Well, 0 fell in that interval. So basically, there's not going to be any convincing evidence here because 0 is contained in our interval. So, does it really matter where Mr. Z puts you in class? Well, based on what we're looking at here, maybe not. Okay. Again, you guys can keep moving through these videos at whatever rate you want. If you're fine just looking at the note key and moving forward, that works as well. You don't have to watch the videos. But please make sure to submit the assignments that are due each day. Look forward to hearing.